In today's lecture, we are going to talk about linear solvers. These are techniques and numerical methods that solve linear systems of equations. So let's start by defining what a linear equation is. A linear equation, by definition, is an equation where the unknowns or variables, that's what you see as x, y, z, etc., show up in a linear fashion. So you don't see x squared, square root of x, log x, etc. And these are a few examples of linear and nonlinear equations. 2x plus 3 equals 0 is a linear equation. Ay plus c is a linear equation as long as a and y are constants and or not nonlinear functions of y. 2u equal 5 is a linear equation where u is the unknown, as opposed to nonlinear equations where you have some examples. 2x squared plus 3 equals 0 is a nonlinear equation because x shows up in a nonlinear fashion. It's x squared. A square root of y equal b, 2 log u equal 5. And the idea of linear and nonlinear is that when you change one quantity, the change in another one is linear. So if you double x, y equal x, for example, is a linear equation because if you double x, y will double. Y equal 3x is a linear equation. If you double x, y will be multiplied by 3, okay? But y equal x squared is nonlinear because if you double if you double x, y is gonna quadruple, okay? So that clarifies what a linear equation is. Now on to systems of nonlinear equations. When you have many linear equations and unknown that are related to each other, so you have two unknowns and two equations, for example, that are connected with each other, then that constitutes a system of linear equations as long as the individual equations are linear. So for example, 2x plus 3y plus 5 equals 0 and 5x plus 3y plus 7 equal to 0. Those equations come together, assuming they're coming from the same system, physical system. They describe a process together where x and y mean different things. Then this constitutes a linear system of equations. We're going to be dealing with systems that have thousands and thousands of such equations. Now, where do these equations arise in engineering? They're pretty much all over the place. Anytime you're trying to do conservation, separations, specifically in my research area in computational fluid dynamics, linear systems are very important in the discretization process and specifically in the solution for the pressure, which is an important quantity in fluid and gas dynamics. Let's start, however, by doing an example from separations to show you a simple way of how these equations come about. You will not be responsible, at least right now, for coming up with the equations themselves. Rather, I will give you a system of equations and we're going to be discussing how we're going to solve that system of equations. So you will not be that much concerned with how these equations came about, at least right now, okay? An example from separations. Separations is a chemical engineering process by which a liquid or a fluid is separated into individual compounds by going through different processes, different stages in the process. And what I'm showing here is an example of a separation. There's a fluid coming in from the left that has three compounds. Let's call those A, B, and C. And we want to separate the compounds, separate A from B and C and so on. And so this fluid goes through the first column of separation and then it comes out A and B without any C on the top. And then at the bottom you have another column that separates A, B, and C. And you see at the bottom you have A and C without any B. Anyway, in this particular configuration, the fluid comes in at a mass flow rate of 10 kilograms per second, and the mass fractions of the compounds A, B, and C are given by 0.2, 0.6, and 0.2 respectively. A mass fraction is simply the fraction of the total mass. So you have 20% A, 60% B, and 20% C. Now, this fluid, this mass comes in and exits at the three other stations. It just so happens in this case that we know the composition of the fluid exiting at these three different stations. We know the compositions of A, B, and C at each one of those exits. Okay. However, what we are looking for are the mass flow rates. So the mass flow rate at station 1, station 2, and station 3. Okay. Now, one thing to note is that the mass flow rate of component I, so that's m dot I, I'm showing here at the lower left of the screen, okay, over here, m dot I is given by the mass fraction of compound I times m dot. So for example, the incoming mass flow rate of A is 0.2 times 10 kilograms per second. So that's the mass fraction of A times the total mass flow rate of the fluid over there. Okay. Now our goal is to find the mass flow rates at the different stations, and for simplicity, we're gonna assign unknown variable names to those mass flow rates. We're going to call those x1, x2, and x3. We're going to have called them m.1, m.2, m.3, or m1, m2, m3, whichever you prefer. It really does not matter. Okay, so how would you suggest we come up with equations for x1, x2, x3? Obviously, we need three equations because we have three unknowns, and if you remember your math correctly, you would need the same number of equations as there are unknowns, same number of non-redundant equations as there are unknowns. So in this case, we're going to start by the global mass conservation idea, is that whatever mass is coming in is going to exit through all of these stations. So when you think of mass is just material coming in, it has to come out from the other side. And so we're bringing in 10 kilograms per second, and a total of 10 kilograms per second should come out. And therefore, we know that the sum of the mass flow rates at the three different stations should sum up to 10. So x1 plus x2 plus x3 should be equal to 10 kilograms per second. Next, we will take one of the components and do a mass balance for that component, and we're going to choose component A. And like we said, the mass flow rate of a compound I equal to the mass fraction of compound I times the total mass flow rate. Now, if you look at A, we know that we have 0.04 times x1, so that gives us the flow rate of A at station 1, plus 0.54 times x2 gives us the flow rate of A at station 2, plus 0.26 times x3 gives us the flow rate of A at station 3. That should be equal to the total A that's coming in from the left, which is 0.2 times 10 kilograms per second. That's what's coming in on the left. Next, we could choose either compound B or compound C, but we'll just go ahead with B. And that gives us 0.93 times x1, that's the mass flow rate of B at station 1, plus the mass flow rate of B at station 2, that's 0.24 x2, plus 0 x3 mass flow rate of B at station 3, and that's equal to the mass flow rate of B coming in from the left, that's 0.6 times 10. And that gives us the three equations and three unknowns. We could have selected to do the mass balance on compound C, but that would give us a redundant equation. So we would have to choose only three of these equations. Okay, now we're going to take these equations together, and we're going to make one step to just simplify the presentation of this system. And so if you remember your linear algebra classes, the way I'm going to write this, I'm going to put all the coefficients of x1 together and all the coefficients of x2 together, all the coefficients of x3 together, and write it in this form. 1x1 plus 1x2 plus 1x3 equals to 10, if you notice, the first row. And then the second row is 0.04x1, 0.54x2 plus 0.26x3 equal 2, and 0.93x1 plus 0.24x2 plus 0.0x3 is equal to 6. All I did was just change the nomenclature. Now that's important because my goal is to write this in a matrix format. And when you look at this, that can be turned into a matrix vector notation. If you do not remember your linear algebra, your matrix vector multiplication, please get a refresher as soon as possible on my website. There's a link to a resource where you can review your basic linear algebra, remember how you do matrix vector multiplication. But in a nutshell, what we're doing here, what we're representing with this notation this matrix here represents the coefficients of multiplying the unknowns x1, x2, and x3 in the above equations, and this can be read as the first row, which is 1, 1, 1, times the dot product of the first row times the vector of unknowns equal to 10. So that gives you 1 times x1 plus 1 times x2 plus 1 times x3 equal 10, just a dot product. And then take the dot product of the second row, which is a vector containing 0.04, 0.54, 0.26, and dotted with x1, x2, x3, that gives you 0.04 x1 plus 0.54 x2 plus 0.26 x3 equals to 2, and same thing, 0.93 x1, 0.24 x2, 0.0 x3 equal to 6. It's just dot products of the row vector times the column vector of unknowns. Okay, now this is very important, that we wrote the system this way, because now we can use the entire theory of matrices to analyze this system of equations. If we left it as it was before, it's just really cumbersome. I mean, you could probably come up with ways to solve it, but if you want to generalize to hundreds or thousands of equations and draw some general conclusions, you have to do a mathematical abstraction. And so happens that the math abstraction over here is to write a system of equations as a matrix vector multiplication. So what we're going to do, we're going to call this matrix over here, we're going to call this the coefficient matrix, and we're going to give it the nomenclature A, boldface. Some people put it in brackets to distinguish it from a vector. And the solution vector, or the vector of unknowns, that's what we're trying to find. We're trying to find these quantities, is given by x, and the right-hand side, which is usually known, is given by the vector B. So now we went from a system of equations to a matrix formulation to actually a general form, AX equal to B. And with that, we can start now thinking about generic ways to solve this system of equations. Obviously, we need to find X. Now, I know some of you have done this in high school and some linear algebra, but entertain the thought process that I'm gonna guide you through. Idea is, how can we solve for x? Well, let's make an analogy with a single equation where you could write ax equal b. Then you typically solve for x by saying x equal b over a. So can we just do the same, x equal b over a? Well, if you remember your linear algebra, division by a matrix is not defined. What do? Do you divide? Do you take the 1 over every entry? How does b over a work? What is the answer? You have a matrix and the denominator and a vector in the numerator, and the result should be a vector. So how do you carry out the division? Well, it turns out that the equivalent of matrix division is to multiply by the inverse. Now remember, the inverse is the equivalent of division. So when you write x inverse, that's equivalent to 1 over x for a single scalar quantity. But for matrices, there's no 1 over. It needs to, the meaning of an inverse is a little bit different. And specifically, the inverse is a matrix such that matrix inverse times the original matrix is equal to 1, or a matrix with diagonals in. Anyway, so that's back to linear algebra. But the point is, when you have a system ax equal b and you want to find the solution x equal a inverse b, the goal of linear solvers, that's where we started at, linear solvers, the discussion of numerically solving systems of equations. The goal of linear solvers is to do one or more of the following, either numerically find the inverse of a, or find an approximation to the inverse of A. And why would we do an approximation to the inverse of A? Well, if you think about it, the vast majority of problems we will be solving in engineering come up from physical models of reality, and those physical models have a lot of modeling errors in them in the first place. Then we take those physical models and we convert them to systems of equations. So you could say, well, you know, we committed a lot of error in the model anyway, so why can't we let ourselves approximate the solution process and live with whatever error we introduce, because very likely the error we will introduce is much less significant than the error introduced in the modeling. So that's the idea behind finding an approximation to the inverse of A, or solve the system without explicitly computing the inverse. So that's where we get into iterative systems, iterative solvers, which we will discuss later in the class. But the idea here is that we will come up with recipes where we do not necessarily directly solve for the inverse of A. We instead we just get to the solution vector X directly. Okay, so now let's go back to our example in separations and let's try to do it in Python. I'm going to give you the recipe over here, and then we will do it together. Just like we discussed last time about modules, basic Python functionality doesn't give you much to work with. However, there are libraries out there that you can use to give you cool, useful functionality. And one functionality we need here is the ability to compute the inverse or solve a system of equations. And that is found in the NumPy linear algebra library. So you do from numpy.linalg, so that's NumPy linear algebra, import solve. The solve function is a function that solves a system of linear equations, and it essentially is like a Gaussian elimination, which we will slightly go over next. And the way you define this matrix, the way you use solve is you give it a coefficient matrix and a right-hand side, and it finds a solution vector for you. So to define the matrix, remember what we did early on in the Python examples. We created a list of lists to define a matrix. In this case, I'm going to define A as a list of rows. Okay, row vectors, so 1, 1, 1 in the first row, 0.04, 54, 0.26, etc. And that defines a matrix. See how I nested 3 lists within one big list. And the right-hand side vector is defined as 10, 2, 6. And then simply you do x equals solve A, comma B. So the solve function takes the matrix first and the right-hand side next, and then you can print x. So let's do this in Python together. I'm going to grab a Python window over here. Okay. And I'm going to do from numpy.linalgebra import solve. So that imports the solve function. Okay. Now, there's a little trick you can use to learn about what the function, what the function that you're importing requires. You can type the function name, solve in this case, and then open parentheses. And if you press Shift Tab, it gives you a description or the function signature. Solve a linear matrix equation or system of linear equations, and parameters A, coefficient matrix, B, ordinate dependent variable values, or the right-hand side. Okay, so let's go ahead now and define A is equal to our 1, 1, 1 matrices, row vector. So let's see what we had in the slides. We had 1, 1, 1 and 0.04, 0.54 and 0.26. My 0.26. 0.26, and then the last row is 0.93, and then 0.24, and then 0.0. So that defines A. Then we define B as 10, 10.0, 2.0, and then 6.0. And then simply we do x equal solve A, comma B. Then if we print x, we get the following solution. 5.823 for x1 and 2.43 kilograms per second for x2. So that's the flow rate at station 2, and 1.74, that's the flow rate at section 3. Okay. Now, there's another way to do this as well, and that's by using the inverse, if you remember your MATLAB. And in this case, we need to import the inverse function from Python, from the NumPy linear algebra library, and then we do A inverse is inverse of A, and then we multiply the inverse by the right-hand side using this at notation. So let's try this together. Again, so from linear algebra, from NumPy dot lin algebra import inverse, and then A inverse is equal inverse, and again if you press shift tab, well, you need to import it first, and then A inverse is equal to inverse, shift tab, inverse of A, and that gives you, so you can print A inverse now, and it's just a matrix with the following numbers in it. Now to get the solution, you simply do x equal A inverse dot B. Now this at symbol is the equivalent of the matrix vector multiplication. Okay, and then print x, and we should get the same answer as up there. Okay, so this at symbol is equivalent to a dot product or a matrix vector multiplication. One other thing you could do is A inverse dot A inverse dot B, and that gives you the same answer as well. Okay, now we come back to our slides, and we got the answer for this. Okay, now let's generalize to systems of equations, and what I'm going to do here is write a very generic system of equations, but behold, I'm going to change nomenclature a little bit. Rather than using x, y, and z, I'm going to follow the nomenclature we used with the separations example, use x1, x2, and so on. And rather than having numbers for the coefficients, I'm going to pick A and give it two indices, ij, and then you will have a system of equations that looks like this: a11 x1 plus a12 x2 and so on, all the way to a1n xn. So we have n unknowns equal to b1, but then equation 2, we switch the indexing. We'll discuss the indexing in a second when we write it in matrix form, so that makes sense. However, know that these coefficients are generally constant, but they're different in general across different equations. However, we have n unknowns here all the way to xn, from x1 to xn, but we have m equations, and m and n are generally, in practice, they may not be equal. Okay, now in general, for a system of equations, an m by n system of equations, so m equations and n unknowns, that you can write in vector form, in matrix vector form, as an m by n matrix. So it has m rows, the matrix has m rows and n columns, and the vector of unknowns is n, and the vector of knowns, or the right hand side, has m values in it. Remember, rows describe the number of equations. Now alternatively, you can write this as ax equal b, or this summation form. I don't think we have to use this summation form for the time being, but know that this summation form, if you untangle it, essentially you specify I, or you specify an equation, you fix I, and then you sum over j's, and that will reproduce essentially each one of those equations. So if I equal 1, that is going to give you equation 1. If I equal 2, that will give you equation 2, and so on and so forth. Or you can go back to the matrix, to the m by n matrix, and just do the matrix vector multiplication. Remember, you take a row as a vector and do the dot product with the unknowns vector, and that gives you the first equation, and so on and so forth. Okay, now let's talk about the indices, the a11, a12, a22, etc. Entries are referred to as aij, I typically refers to the row or the number of the equation. Which equation are you doing? First equation, second equation, so on. And J refers to the column or the unknown that is that you're looking at. Okay, so Aij, I refers to the row, J refers to the column. But you know, that nomenclature also confuses me myself. So if you forget that nomenclature, use the following nomenclature, which I personally use. I call it ARC, A-R-C, where R is the row and C is the column. So next time you say A for 3, that tells you this is the fourth row or the fourth equation, and column 3 or the third unknown. Okay? Now that's for a general system of equations. Again, the abstraction here being that we took a full system of equations and wrote it in matrix vector form. Okay? Now, to be well posed, what is the relationship between M and N? Well, we just kind of alluded to this earlier. If you have 4 unknowns, you need 4 equations to solve for those unknowns for the problem to be well posed. Same thing, if you have 50 unknowns, you need to have 50 equations. So for an m by n system of equations to be well posed, the matrix or the number of equations need to be equal to the number of unknowns. In other words, m is going to be equal to n. And from here onwards, we're only going to assume that we have well-posed systems of linear equations. And in other words, the matrix is of size n by n. So you have n equations and n unknowns. Okay, so n is just an arbitrary, it's just a dummy variable for the number of equations you're dealing with. But if I give you a system of 10 equations, then you expect to have to be solving for 10 unknowns. Okay. Now, throughout your career as a chemical engineer, as an engineer, as an engineering scientist, as a researcher, as whatever you end up doing with a degree in chemical engineering, you're going to be facing some common matrices. We're going to just skim over those very briefly so that we just expose you to these matrices. We're starting by the first one on the upper left corner. A dense matrix is a matrix that is pretty much full. It doesn't have any zeros in it. An upper triangular matrix, on the other hand, has only non-zero entries on the main diagonal, which is that diagonal A11 all the way to ANN, and upper. Everything below the diagonal is 0. So entries that are missing over here are actually 0. A lower triangular matrix, on the other hand, is the opposite of an upper triangular matrix. You have the main diagonal, and below the main diagonal, all entries are non-zero. A diagonal matrix is one where the main diagonal is non-zero. An identity matrix is a matrix where the main diagonal contains only ones in it. Now, A inverse times A gives you an identity matrix. Now, the most important matrix that you will very likely be dealing with if you end up doing numerical simulations is a banded matrix, and that is a matrix where you only have a few diagonals that are non-zero. You'll have the main diagonal, upper diagonal, first upper diagonal, and first lower diagonal non-zero, and so on. We will be looking at this equation very shortly. Okay, so now we had said that the goal of linear solvers is to either find a solution to A inverse, an approximation to A inverse, or find the solution vector x without directly calculating the inverse of A or the approximation of the inverse of A. We will distinguish between 2 key solution methods or solution approaches. And the first one being direct methods, where these are general approaches to solve an arbitrary system of linear equations, whether being dense, upper triangular, lower triangular. However, these methods will directly solve the system of equations. There's no iterations involved. You just immediately get the inverse and get the solution in one shot, as opposed to iterative methods where we're not going to necessarily directly or compute an exact answer. We're going to just start with a guess and improve on this guess until we are satisfied with an answer down to a certain tolerance. Now, iterative methods are actually very effective and much cheaper for very large sparse matrices, which we will discuss a little bit later. But sparse matrices are essentially plenty of zeros in the matrix. So pretty much the matrix is nearly empty except for a few diagonals and few terms scattered here and there. Iterative methods are much more effective and faster because they allow us to directly deal with the solution without having to store the matrix, etc. Now let's dig a little bit deeper into direct methods. The first direct method that you learned in high school is Gaussian elimination, and that's essentially an algorithm to solve any system of linear equations, whether be it sparse, dense, upper triangular, whatever. It's a general algorithm to find a matrix inverse. Essentially, it's essentially a methodic approach to solving the equations by hand. The cost computationally scales as n cubed, where n is the number of equations, and that's very expensive. So the number of operations is essentially n cubed. So if you have 100 equations, you would have 100 to the power 3 operations you have to do to get to the answer. LU factorization is useful when you want to solve AX equal B for different B's, but for the same A. L is a lower diagonal matrix and upper triangular matrix. U is an upper triangular matrix. Determining L and U is expensive usually, but you have to do that once, and then you can reuse those as you change B. TDMA, PDMA stand for the tridiagonal matrix algorithm and pentadiagonal matrix algorithm. Those are very efficient direct methods. In fact, they're pretty much the only efficient direct methods, but they only work for what we call tridiagonal and pentadiagonal matrices. More on that in a second. And finally, fast Fourier transform solvers. These are also efficient direct solution methods, but only work for problems that are periodic or don't have boundary conditions. Now, in this class, we will learn about only one direct method, and we will go ahead and implement that method. You learned about the Gaussian elimination and possibly LU decomposition, and you're welcome to try to implement those on your own. But for our intents and needs as chemical engineers, we're going to look at the tridiagonal matrix algorithm, and it's a very special and efficient direct method for tridiagonal matrices. Okay, so what are tridiagonal matrices? These are matrices that have only 3 non-zero diagonals: the main diagonal, the first upper diagonal, and the first lower diagonal. These matrices arise typically from the solution of boundary value problems such as heat and mass transfer, and we will do an example of heat transfer and see how we end up with a system of equations like that. But they're very common and popular. Now, the beauty of this tridiagonal matrix is that we don't need to store all the entries in the matrix. Think of the matrix; it has n by n entries, right? Because you have n equations and unknowns, so it has n rows and n columns. So the total number of entries that you have to store, the total number of coefficients that you have to store in memory is n squared. Okay. However, for the tridiagonal matrix, you don't have to store all the entries because it's pretty much all zeros. All you have to do is store the main diagonal, which contains n entries, and then the first upper diagonal, which contains n minus 1 entries, and the first lower diagonal, which contains n minus 1 entries, right? For a total of 3n minus 2 non-zero entries, right? The main diagonal has n entries, the one above it has n minus 1 entries, the one above that has n minus 2, etc., all the way to a single entry. Now, what's nice here is that you can store this array, this matrix, very efficiently. And we change the nomenclature a little bit now. We're going to call the main diagonal entries as D's, and we'll change the nomenclature from A11, A22, etc. to D1, D2, all the way to Dn, enforcing the idea that this has n entries. Now, the main diagonal has n entries. The upper diagonal, we're going to call it U, that contains U1 all the way to Un minus 1, and the first lower diagonal also has n minus 1 entries, and we'll call those L1 all the way to Ln minus 1. Now, if you think about it, L, D, and U, they're just vectors, okay? So all we have to do is store those vectors and somehow manipulate them without having to deal with the array. What I'm going to show you next is the algorithm. We're not going to derive it, we're just going to show you what the algorithm looks like, and it's called the tridiagonal matrix algorithm, TDMA, also known as the Thomas algorithm. And given a lower diagonal, upper diagonal, main diagonal, and the right-hand side. So these are vectors. All you need to know about the system are the non-zero vectors, and say this is the main diagonal, this is the lower diagonal, this is the upper diagonal, and this is the right-hand side. So given L, U, D, and B, so L is lower, U is upper diagonal, D is main diagonal, B is the right-hand side, you do the Thomas algorithm in 2 steps. Okay, starting with I equal to all the way to n. So this is going to be based on index 1. We're counting from 1, okay, for simplicity. Starting with I equal to all the way to n, you start by changing the d's, changing the entries in the main diagonal, and you go with a di equal di minus ui minus 1 li minus 1 over di minus 1. So d2, for example, would be equal to d2 minus u1 l1 over d1. You don't touch d1 because we're starting from 2. d3 would be equal to d3. So the new d3 is equal to the old d3 minus u2 times l2 over d2. Now, what are u2, u1, etc.? They're just the entries in the vector, right, of the main diagonal and the upper diagonal. Next, you go to b, and same thing, bi is given as the old bi minus bi minus 1 li minus 1 over di minus 1. Okay, and make sure you use the most recent values of di. Okay, so step 1, you start with di, then do bi, and you go 1 step at a time. Okay, next in step 2, we're going to find the solution x. We're going to start with the end, so start with xn is given by bn over dn. So if you have 5 entries, 5 unknowns, x5 is b5 over d5. Now remember, d and b's have been modified over here. We're no longer using the input diagonal and right hand side. We just modified them, so make sure you use the most recent values. And then we go through all the x's starting from the end again. So we start at xn, then we go from all the way from n minus 1 to 1, and xi is given as bi minus ui xi plus 1 over di. So for example, x4 would be equal to b4, again the most recent value computed here, minus u4 times x5, which we just computed here, over d4. Okay, now you will find many different flavors of this algorithm. They are essentially all equivalent. Okay, let's do an example, and this is by hand, an example by hand. Eventually we're not going to do this by hand, but it's just good to give you an illustration of how this works. And the question is, solve the following system of equations by hand using the Thomas algorithm. And you're given 2x1 minus 3x2 equal minus 4, x1 plus 2x2 minus x3 is 2, etc., etc. Okay. So now the first step is to write this system of equations in matrix form, and I'm going to leave the equations as is. So the coefficient matrix would be 2, minus 3, 0, 0, and then 1, 2, and then minus 1, 0, and then 0, 4, minus 1, 1. So that would be x underscore 4. There's a little typo over here. Let me fix that. Okay, x4 equal 9, and then 2x3 minus x4 equals to 2. And you see how this is constructed. The way you could do this is start by writing out the column vector of the solution vector of the unknowns, x1 all the way to x4, and then build your matrix. It's pretty straightforward. Now to use the Thomas algorithm, we need the 3 main diagonals, L, which is 1, 4, 2. So L1 is 1, L2 is 4, L3 is 2. The main diagonal has 4 entries, right, because it's a 4 by 4 system. And the entries are 2, 2 minus 1, minus 1. So D1 is 2, D2 is 2, D3 is minus 1, D4 is minus 1. And for the upper diagonal is minus 3, minus 1, minus 1. They're just the diagonal vectors. And we also need B, the right-hand side vector, is given by minus 4, 2, 9, and 2. Okay, next we implement the TDMA. Remember that step 1 said, we leave D1 untouched, but we start at 2 and then go all the way to the end. And we have the following recipe. DI, we change DI as DI minus U minus 1, L minus 1, DI minus 1, etc. So starting with I equal 2, we're going to find that D2 is equal to D2 minus U1 L1 over D1. Now, what is D2? You look at the D vector. D2 is equal to 2. And minus U1, what is U1? Is minus 3 times L1, what is L1? Is 1 over D1, right? So what is D1? Is 2. And then you get 7 over 2. Now we go to B2. B2 is equal to the old value of B2, which is 2. Okay, minus B1 L1 over D1. What is B1? Is minus 4. What is L1? It's 1. And what is D1? It's 2. And you get 4. And so on. You repeat for I equal 3. You repeat for I equal 4. And make sure you use the most recent values that you have computed. Okay, so for example, in the calculation of B3, we have B3 equal B3 minus B2 L2 over D2. Now, what is this B2? You just computed it. It's up here. It's just in the line above it. It should be actually 4 over here, and that is a typo, over D2, and that D2 has been just computed as 7 over 2. Okay, and then L2 is 4, so this should be minus 4. There's a typo over here. Okay, and same thing over here. B3 is the most recent value, 31 over 7. There's just a typo over here. This B2 should be equal to 4. Okay, now step 2 of the algorithm is we start from the end. Xn is equal to Bn over Dn. Start from the end, so that's x4, gives us x4, and then we continue with the remaining x's. Excuse me. So at I equal 4, so we start at x4, that's b4 over d4. Now what is b4? It's minus 60, we just computed up here. Over d4, we have it here, minus 15, and that gives us 4. Same thing for I3, it's b3. For I equal 3, x3 is b3 minus u3 x4 over d3, and b3 is 31 over 7, minus u3 hasn't been changed, that's 1. And what is x4? We just computed it. That's 4 over d3 from over here, 1 over 7, and so on. It's just really annoying algebra. But once we implement it in a code, it will make a lot of sense, make things easier. Okay. Now the question is, what types of errors are present here? Iteration error, round-off error, truncation error. Well, there's obviously no truncation error because we were given a system of equations. We don't know where those equations came from, and so as far as we're concerned, there's no truncation error. Is there iteration error? No, there's no iteration error because we did not iterate. We just hit the solution directly. There's no repeated calculation. We just solved for x4, x3, x2, and x1. Is there round-off error? There could be if we were not dealing with integers. We carried out exact arithmetic over here, but if we were doing this numerically, there would be round-off error. Anytime you do a calculation that is not exact on a computer, you're gonna have to deal with round-off errors. Okay? Okay. So now, obviously, we need to do this for very large systems of equations. And in practice, we deal with large systems. So it would be ridiculous to attempt a solution by hand for large systems. So we need to first be able to use the Thomas algorithm. We need to be able to program the representation and solution of such large systems of equations. And we will use Python to the rescue. Okay? Now, to be able to, the Thomas algorithm dealt directly with the diagonal vectors of a tridiagonal matrix. So in principle, we know how to do this. All we have to do is create these diagonals and then run the Thomas algorithm. But it just so happens that in many cases, these tridiagonal matrices have a certain structure that is somewhat repetitive. So here's an example of a matrix that you get from a heat transfer problem. This is only 5 by 5, but you see there's like ones and ones on the upper and lower diagonal, and there's -2 on the main diagonal except for the first and last points. And this will happen even for a 1000 by 1000 matrix, okay? So for the tridiagonal matrix, we only care about the non-zero diagonals. And an efficient method would be to just create the non-zero diagonals as simple 1D vectors. As far as the Thomas algorithm is concerned, we only need the main diagonal, upper and lower. But to be able to compare kind of with exact solutions, it would be nice to be able to construct a full matrix and give it to Python to give us an exact solution. So we want to learn how to do that right now. Again, like I said, it would be nice to create the non-zero diagonals as simple 1D vectors and then somehow tell Python that those are part of a matrix with the rest of the matrix being 0. Now, there's a function in Python called diag. There's an equivalent in MATLAB. It comes from NumPy, and it does that exactly. And it's defined as diagonal vk, and it creates a dense matrix with the vector v on its kth diagonal. So think of this again. You create a vector. Let's say you pick this -3, -2, -2, -2, -1, and you call the function diag v, that vector -3, -2, -1, and put it at the 0th diagonal. That's going to create a full matrix, okay? A dense matrix is going to fill it with all zeros, okay? So the storage is going to be is going to take a lot of storage. However, the only non-zero elements are those given by v on the kth diagonal. If k equal 1, that's going to be the upper diagonal. K equal -1, that's going to be the lower diagonal. K equal 2 equal second upper diagonal, and so on and so forth. Okay, so here are some examples with Python. So on the first one here, from NumPy, import diag. That's how you call the diagonal function. Next, we're going to create a NumPy vector that contains 1, 1, 1. So far we had only dealt with lists. Those are square brackets with values in them. Right here, I'm introducing something from NumPy called the NumPy array. Okay, and that NumPy array is called as array, right? Now what I'm missing here is importing NumPy as NP, so you'd have to import NumPy as NP. That's a typo over here. But assuming that you've imported NumPy as NP, you declare v as NumPy.array and just give it the list that we are used to using. So we're kind of taking things up a notch here. We're going to start using NumPy arrays rather than lists, but all you have to do is take a list and wrap it in an np.array, and that gives you a NumPy array. Now I create A as diag v, that's our vector, and I want to put this on the main diagonal. So A is diag v0, that gives you a matrix, mostly zeros, except for the main diagonal has the vector v. Same thing, if we'll keep the same v, but now let's put it on the first lower diagonal, so K is -1. And you see here when we print A, we get the entries on the lower diagonal. Same thing with the upper diagonal. We change K to 1. But notice what happened here. The matrix that's being created has to be consistent with the number of entries, because usually the matrix, because a matrix, n by n matrix, has n entries on the main diagonal. In other words, a main diagonal with n entries is going to create an n by n matrix. So 3 entries on the main diagonal will create a 3 by 3 matrix. However, n entries on the first lower or first upper diagonal will create an n plus 1 times n plus 1 matrix, right? So here we have 3 on the first lower diagonal, which means we have 4 on the main diagonal, which means the matrix is 4 by 4. So just be cognizant of that, of the size of the matrix. Now, if these matrices are of the same size, so let's suppose here we created a 3 by 3 and a 3 by 3 and a 3 by 3 matrix, we can add those. Just like we add two numbers, we can add these matrices to create a matrix that has a lower, upper, and main diagonals that are non-zero. And that's how you would do this. So again, from NumPy, import diagonal. The main diagonal, I'm going to call it D. It contains these values, -3, -2, -2, -1. It has 5 entries because this matrix is 5 by 5. And an upper diagonal, 1, 1, 1, 1, has 4 entries. Lower diagonal, 1, 1, 1, 1, has 4 entries. And then all we have to do is add those together. So we will do the diagonal for the full A is equal to the matrix with the lower diagonal plus the matrix with the main diagonal plus the matrix with the upper diagonal. Remember, each one of those is a matrix in and of itself. And adding them will add, as long as they are of the same size, it will add one entry at a time. Okay? All right, so let's go ahead and try this out. So from NumPy, import diag, okay, and import NumPy as NP. Okay. Now again, we could use in this recent example, I didn't use NumPy.array, so we could avoid using that if you like. So let's just not use it for the moment. Okay. So okay, and let's play around. Say v vector is 1, 2, 3, 4, and then if you do diag v0, it will create a matrix with v 1, 2, 3, 4 on the main diagonal. If you do diag v minus 1, it will create a matrix with 1, 2, 3, 4 on the first lower diagonal, but now the matrix size is 5 by 5. 1, 2, 3, 4, 5. Okay. Now let's say diag v minus 2, it will create it on the second lower diagonal, and now it's a 6 by 6 matrix. Notice the main diagonal is zeros, the first lower diagonal, and then the second lower diagonal. Same thing, diag v1, we'll put it on the upper diagonal, and so on. Now, to do the tridiagonal matrix, I'm going to declare the main diagonal as, let's say 1, 2, or take the example we did in class, -3, -2, -2, -2, -1. And the upper diagonal is 1, 1, 1, 1. And the lower diagonal is 1, 1, 1, 1. And then we do the total A is diag. We're going to place the lower diagonal at -1 plus main diagonal at 0 plus upper diagonal at 1. And then we print A, and that gives you the full matrix. Okay, that gives you a full matrix. Now, again, remember, for the Thomas algorithm, all you need is D, U, and L. So you really don't need to write this in full. But if you so happen, and that's what we will be dealing with, we're going to compare our solution from the Thomas algorithm to the solution directly given by Python using the solve function. You're going to need to be able to do the full matrix. So for example, if you want to compute the inverse to do A inverse B, you would have to do inverse A, and that would give you the inverse of this full matrix, okay, rather than just taking the one diagonal at a time. Okay. All right, let's go back over here. Okay, notice how these diagonals are consistent. Okay, now to generalize this to an arbitrary number of equations, like I said earlier, in many problems in heat transfer, especially with tridiagonal matrices, you will notice that the matrix structure is pretty much the same. Like for the 1D heat transfer problem, you will probably have -2s on the entire main diagonal except for the first and last point, and you'll have 1s below and 1s above it. So obviously we need a way to generate these lists, like we did the upper diagonal, lower diagonal, and main diagonal. We need a way to generate those for an arbitrary number of entries, n. Okay, say n is your number of equations and number of unknowns. Okay, and you can do this, you can automate this with a function from NumPy called ones, just like, you know, in MATLAB you had zeros and ones, I suppose. Same thing in Python. There's a function called ones, and it takes only one number, n, and creates a vector of size n that contains the value 1. So if you call ones parentheses 3, it's going to give you an array that has three entries with a value of 1. And if you wanted to create 5 of those, you do ones 5. Okay. Now to create, we're going to take this function and use it to build non-trivial matrices. So to create non-trivial values, we can multiply the function ones by a desired value and then adjust the entries as needed. So for example, if you want to create a main diagonal that is mostly -2's, you just take -2 times ones, however many entries you want, and that, in this case, ones 5 entries gives you -2, -2, -2, 5 times. And then you go ahead and adjust d at the first point and last point. You do d0 is equal to -3. So it changes the first entry in the matrix. Now to change the last entry, you could access the last entry index, which is in this case 4. So you could do d4 equal -1, change the last entry. Or if you want to be smart about it, rather than to use the last index, you need to know the size of the array. That sometimes can be confusing to you. Instead, rather than doing this, there's a really cool Python nomenclature, and you use simply -1 to start indexing from the end. So when you use a positive index on a vector in Python, you start indexing from the beginning, from 0. So d0 is the first entry, d1 is the second entry from the beginning, from the left. Now, if you use negative entries, if you do -1, gives you the last entry, or you start indexing from the right. And so d-1 gives me access to this last entry over here, and then I change it to -1. I could do d-2. It gives me the second entry from last, and I can change that as well if I need to. Okay. Now, with this in mind, we can do this for an arbitrary number of points. And so let's go ahead and try this. And we're going to import. So from NumPy, import diag and ones. Okay. And then we're going to define n. Let's say we want 10 entries. Okay. Now I want to create the matrix. So let's do the matrix we just discussed in the slides, where you have -3, -2 on the diagonal, etc. Okay. So my lower diagonal L has ones of size n-1. My main diagonal D has mostly -2 times ones, okay, of size n. Now I need to fix the first and last entries. And that would be d0. It will fix the first entry, and I'm going to call this -3. Okay, and the last entry, so let me prove it to you. So first print d. So d is -2, -2, -2. Okay, and then as expected, it has 1, 2, 3, 4, 5 entries. And then I'm going to go d0. So what is d0 is, well, I already had made that change. Okay, d0 is -2, and then if I do d0 equal -3, and then print d, it changes the first entry. Now, what is d-1? It's the last entry from the end. It's -2. Okay, so I'm going to change that to -1, and then print d, and notice how it changed the last entry. Now, d-2 is indexing from the right-hand side. Okay, is d-2 is -2. I don't need to change that. Okay, so now I'm gonna put these together over here, and then do z0 is -3, and then d-1 is equal to -1. Okay, and finally the upper diagonal is ones and of size n-1, and the full matrix A is diag lower -1. Put the lower diagonal, first lower diagonal, plus diag d at the main diagonal, plus diag upper at the upper diagonal, then print A, and that gives you your A. Okay, so go ahead and try it. This is really cool because now you can generalize this to an arbitrary number of terms, and you will notice that this matrix will actually remain unchanged except for the first and last points for any number of points when we do this problem next week. Okay, so if you can do it for 50, and you'll get a 50 by 50 array. And then you can operate on this array A or use the Thomas algorithm. Okay, so next week, next lecture, we will do a serious example, heat transfer in a rod, and see how the TDMA or the Thomas algorithm applies in real life, and how efficient it is. Just don't forget to fix the first and last values on the main diagonal. But with that, we conclude the lecture for today, and we will see you next week. Thank you.